I don't know. Let's find speakers. Bjarke. You have no way of knowing your poster. From Colombia, working with Corey and he'll talk to us a little bit more about 2D. We're progressing now. All 2D will be going back and forth. So once again, please ask questions. And thank you, Bjarke.
Thanks for having me. Yeah, so I'm standing in for Corey Dean, who is the PI sitting next to Jim at Columbia. My office is right in front of all of Jim's furnaces, so I'm risking my life coming to work every day, just for the sake of 2D materials. So I'm going to give a talk that is a bit of a warm-up to all of this moray physics you're going to hear about later this week. I'm going to talk about all of the work we did in the past, trying to do what you can now do with moray materials. It really came out of nowhere, like a lightning bolt from a blue sky, that you could make these nice 2D superlattices by just twisting 2D materials. But the reasoning behind doing it is nothing new. People have been trying to do this for decades. So right now, I'm at the Columbia University in New York. Previously, I was in Denmark at the Technical University of Denmark, working on nanostructured graphene. So the idea is that if you do something particular to graphene, you can change fundamentally its properties. It's fun being in New York. It's a city that is 1.5 times larger than my country, very densely populated. Enjoyed a lot. So graphene, a lot of excitement about graphene. I just wanted to briefly go through why we are excited about graphene and why we want to change the properties of graphene, even though it already has some magnificent properties. It's the strongest material known to man. It conducts better than copper. It is a better heat conductor than silver. And it has this kind of interesting electronic properties. So as a physicist, we don't talk about orbitals so much. We talk about band structures when we want to talk about electronic properties. So here you see what's called a band structure. You have allowed energies on the y-axis, and then you have momentum on the x-axis. So normal graphene is boring in the sense that there's always allowed energies. You cannot turn off graphene. What you really want to have is a slight tweak to graphene. If you could just somehow open a small range of energies where no states is allowed, then you can start to do electronics and more interesting things with graphene where you can really turn it on and off. But the issue here is that you can't just do that. You can just wish for bands to appear at will, because you have what's called the band structure, which is really a fundamental property of a material. It's kind of like the fingerprint, the quantum DNA of a material. It is akin to alchemy if you want to change what goes on with the band structure. And the band structure tells you more or less everything that you could dream about knowing of a material. It tells you whether or not it's a metal, a semiconductor, an insulator, a superconductor. It can tell you things about the mechanical properties of your material. And then a lot of derivative quantities, such as whether or not you can use it as a specific sensor or a transistor, solar cells, and so on. Even qubits, you need specific material properties to make good qubits, or the grounding materials of the qubit at least. So in the past, I was working on trying to make graphene a semiconductor. So this is what I just mentioned. We want to somehow have a range of energies in graphene where connectivity is turned off. So the framework of all of this is what's called band structure engineering. So maybe you can do things to your material that fundamentally changes how it behaves. So it's not just some effective change, it's really the intrinsic properties that you're changing. And effectively, you're making a new material when you are changing the band structure. It is something new as soon as the band structure is different. So in band structure engineering, you can imagine you have some band structure that you calculate. Let's see. Okay. You have some calculated band structure that you would like your material to have. You can then go back and ask yourself, what's the kind of positions for the atoms? What are the type of atoms we need to have this change in the band structure? We just heard a nice talk about the chemist approach to band structure engineering that is looking at the periodic table and then changing the elements of your lattice. The physicist approach is to maybe go in and take a given material and stretch it, strain it, maybe etch away atoms, or maybe change the periodic potential, the local environment your material is living in. So this is akin to like solid state physics 101. You take a nearly free electron, you get some parabolic band structure, the first of these curves on the right. And then when you add a periodic potential to that, the band structure changes. Suddenly you have band gaps opening up, and your material is fundamentally different. So these concepts of changing the position of the atoms, changing the local potential environment, to change the fundamental properties is the physicist approach to band structure. The work I did previously was the brute force approach. So what if we take graphene and we just remove atoms in a periodic lattice? What happens? What happens is that you actually open a band gap in the graphene. So that's a range of energies no longer allowed. And the size of this band gap depends on how big the holes are in the graphene that you're making. So these are called graphene antidot lattices. So you have holes of missing graphene. So that's an antidot. And this is all done in theory. So there was a lot of really interesting work in this direction. It's easy to do these things on the atomic scale if you're just doing calculations. But because graphene had so much potential as a next-gen electronic material, there was a lot of effort to actually trying to realize this in practice. And this is something you can do with 2D materials. You can go in and easily remove the atoms, and you can easily go in and change the local electric environment because all of your bulk is exposed immediately. It's not like a 3D material where having a nice periodic potential throughout something that is a millimeter thick, it's just not feasible. And the same way for making nice arrays of holes or patterning your material in some way, it is much, much harder to do for 3D materials. So 2D materials was really a game changer in this in the field of band structure engineering beyond just theory. So for these antidots, we would engineer the band structure, as I said, by changing the position of atoms and really removing atoms. So from a theory perspective, once you do this in graphene, you can start to play tricks about missing holes. So that's like an anti-dot. You take 2 of those, put them together, and you can make very robust qubits. So this turns out to be like a very robust 2-level system. So depending on how you apply potentials to this kind of a structure, you can have a qubit living either in the missing hole underneath or on top. And you can start to play even more tricks to graphene. You can make electronic waveguides. This is all in theory, of course. Electronic waveguides where part of the graphene is a semiconductor, part of the graphene is a conductor, and you can change how much of a semiconductor it is, depending on how you shape your material. And as I said, once you change the band structure, you change the fundamental properties. So you can engineer the electronic properties, plasmonic, optical properties, whatever you want to call it. A very powerful approach. But out of nowhere came more ray physics. Yeah, sorry, go ahead.
Before you go on to this, I wanted to ask you, so it's a theory, but practically speaking, what would you do? You want to like just shoot ion beams through this? I mean, how would you propose to actually manufacture such a?
So that's going to be the bulk of my talk. All of the different approaches we try to do this, why it's hard to do, why it's dirty, why it's hard to scale down to, like here you can count atoms. This is not something we can do in the lab. We try to scale down, make things ordered. It's going to be a long talk about all the things we tried that doesn't work, but these techniques are improving. So that's why it's worth to keep in mind. But yeah, good point. Yes?
So Is the procedure reversible?
No, not that we know. Maybe you can. I don't think it is. It's hard to grow graphene once you already made these defects in it, and it's not sitting on some growth substrate. Right.
So you're trying to open a gap, right?
Yeah.
So just to take advantage of like graphene having like large mobility.
Yeah.
But why do you have to kill it, right?
In principle, if you could do something that is, atomically perfect, the mobility is preserved. But if the holes that you're going to make in the graphene is kind of disordered and like messy, you have process residues on the graphene, for sure you're going to kill mobility.
Okay, so you put HBM or something on.
Exactly. So that's what we ended up doing in the end. I don't think I have that slide in right now, but I have a nice overview of the minimum feature size, like a literature review. The minimum feature size people made in graphene and then mobility. And it just plummets as you make it more and more dense. But HBN is the saving grace, because then all of your processing is kind of done remotely. Yes?
I know this is just kind of a theory here, but with these holes in the graphene, even if you were God and could cut those out, there would still be strain around these. Is that an ingredient that's under consideration?
Usually not. Usually this is a DFT calculation where you don't consider lattice relaxation. You just remove some atoms and you look at the band structure. And I think that's going to be a bit of strain because you have under-coordinated carbon.
So how could this might end up being a weird squished or stretched hexagon?
I might misremember, but I think if you passivate your graphene with hydrogen, then that kind of helps to preserve the edges and the bonds you're getting there. There are other things you can put to edges of graphene, like OH and fluor, for instance. But the go-to in terms of calculation is just to put some hydrogen there, and then things are pretty stable. In theory, right? In practice, it's hard to control exactly the time of the edge termination you get for these kind of things. Okay, so we were working on this for many years, a lot of slow but steady progress. And then out of nowhere came this paradigm of, you want the super lattice, just, take two crystals and rotate them relative to each other. So here you have graphene sitting on boron nitride. You can see as one of the two crystals are rotating, there's some maximum wavelength you're getting out. Whereas in the case of this guy, which is not animated for some reason, graphene, the lattice constants are identical, so the wavelengths go to infinity as you have zero misalignment. That's it. It does that. So you can control what is the wavelength, what is the periodicity you're getting out of the superlattice, just by how much you control it, the twist angle. So here you have twist angle on the x-axis, and you have the resulting wavelength on the y-axis. And it turns out that this 10 nanometer regime is really where you want to be to see interesting physics in graphene and other 2D materials. And with conventional techniques, we were at the 40 nanometer regime, and like shaving off 1 nanometer at a time to get there. So this was a game changer. It was, as I said, simply not possible to do these length scales before Moraes, but I'm going to talk to you about how we tried at least. So I'm going to show you this, put a bunch of different techniques into this empty space. We have long range order on the x-axis. This tells you something about if you make a superlattice in graphene or your 2D material, what's the length scale over which domains occur or defects occur and things get messy. And then you have the resolution, or this is really going to be the superlattice wavelength that you can get out from this technique. And there's usually two approaches. These are like old nanotech terms when nanotechnology was something that was cool. You can either do top down, so you take your some material and then you carve out a superlattice in that. Or you can do bottom up, where you're really taking some individual constituent material and you make it form a superlattice, so it self-assembles. So there's a bunch of different top-down techniques. So the most famous and most versatile one is e-beam lithography. They use electrons to tune the solubility of some resist. There's focused ion beam lithography. Now we're down in resolution, but the long-range order is starting to drift. You can do what's called scanning, tunneling electron microscopy. This is basically e-beam lithography, but optimized heavily for very small spot sizes. And there's the new kid on the block, which I think is quite exciting, which is an AFM, so atomic force microscope-based technique, where you locally heat your sample with a tip and you can evaporate material away, which gives you very high precision and potentially kind of get us into this area of interesting superlattice physics. Then from bottom up, we have what's called block copolymers. We have self-assembled nanospheres and these kind of things. So the order of business has been for the self-assembled materials to improve the long-range order. The periodicity is already good. And for the top-down techniques, long-range order is perfect, but we need to have better spatial resolution. And then out of nowhere came Moray materials, upended everything we were doing, because suddenly, just depending on how much you twist your material, bam, you reach 10 nanometers resolution. You have barely decent long-range order, and you're just barely touching this area of interesting superlattice physics, which is enough to, like every issue of Nature and Science, there's 5 new Moray papers, and we're not even at the length scales and disorder levels where it gets super interesting yet. Yes.
Right. You don't have a unit on long-range order. Can you sort of give an idea of lateral dimensions of some sort? So what's good enough here?
So for me, good enough would be, let's say, a few by a few microns. So that's where we can like sit down, do electronics, and find something suitable. It just so happens that all of these self-assembled techniques, usually the order is on the range of like 100 nanometers, like 10 unit cells or something like that, and then you get a domain. For industry applications, it's another scale. You want probably a wafer scale order, but for now we are just doing prototyping. But even for prototyping, these guys are too disordered for electronics at least. So quickly, 3 parts of the talk: top-down techniques, bottom-up techniques, and then some hybrid approaches, which is including Moray physics. So quickly, graphene, that's going to be the benchmark material for band structure engineering. As I already mentioned, this is how the band structure of graphene looks when you don't do anything to it. You're going to see a lot of pictures of the band structure, the graphene where we apply magnetic fields. That's like a tuning knob to really let us know, are we changing the electronic properties? So when you put a magnetic field of the graphene, you split the band structure into individual energy levels, and you get graphs that look like this. So you have magnetic field on one axis, on the y-axis, and then you have energy basically on the x-axis. And what we're looking for in graphene that is behaving as it should is just straight line intersecting 0. If you see something that doesn't look like this, you have done something to the band structure of graphene. So this is going to be the smoking gun for some of the slides I'm going to show now. Straight lines intersects approximately at 0. So first technique, e-beam lithography. This is the workhorse of almost any graphene lab if you want to do devices. You have some kind of a substrate. This could be silicon oxide. It could also be your 2D material of choice. And you spin coat a polymer on top. We call it a resist. And this resist, this polymer, consists of a bunch of entangled polymer chains, very long chains, very hard to dissolve. But what you do is you come in with your electron beam. So this is a tool where you program exactly where this very narrow beam of electrons are hitting the sample. And in the spots where the electrons are hitting the sample, the chains with a certain chance get cut off. So this is called chain scission. This is the basic principle of all modern e-beam lithography. You destroy parts of your resist. You get a bunch of effectively the same polymer, but just cut into smaller chains, which is much easier to dissolve. So now when you take this resist and you dip it in some kind of a suitable solvent, you selectively remove the parts of the resist that has been exposed to the e-beam. Then you can do what we call a pattern transfer. You can then etch into your wafer. You get something like this, some sub pattern into your underlying substrate. You strip away the resist, and you are done, basically. So this could either be done into your graphene or some intermediate substrate. We did this, so this is the work I did in the past. As I mentioned, or was asked about, BN really played a key role. So what you have here is graphene sandwich here in between boron nitride on top, on bottom. There's some graphite underneath. So this is almost what Jim calls a generation 4 device, but probably closer to 3.5. There's some graphite on top. And we were able to make fairly small holes into the top boron nitride and then etch that into the graphene. This is an SEM image of an actual sample. Periodicity is something like 35 nanometers. If you look in the part of the graphene where we didn't make any holes, you see these straight lines. Everything looks more or less typical as it should. We accidentally had some Murray physics going on, but just pretend like that didn't happen. And then if we compare that to the part of the graphene where we punched holes, so we tried to change the band structure into something where there's a band gap, suddenly the situation is quite different. These energy levels that always intersect 0 and are straight lines are now curved, intersecting at non-zero. And this blue region here for low magnetic fields, that's low conductivity. So that's actually the presence of a band gap that then changes as you turn on the magnetic field. And this is complex behavior that is hard to have a hand-waving understanding of, but it all matches theory. So we were happy. We showed that you can actually make a band gap in graphene and do band structure engineering. But we were really limited to this 35 nanometer length scale, and we wanted to go to something like 10. Many other people have been pursuing this approach. Yeah, you can also directly measure the band structure in what's called nano RPS. You get a real snapshot of the band structure, and you can show that this is how pristine graphene is supposed to look. And then for the nanostructure, there's a loss of spectral weights up here, which is how it's supposed to look in nano RPS if that's a band gap. All is good. You can do other things instead of directly patterning the graphene. So you're not removing atoms, but you want to change the dielectric environment. Maybe you want to pattern your backgate. So this is similar to some of Jim's slides, where there's graphite on top, graphite underneath. But here the graphite close to the graphene has a pattern, a structure to it. So when you apply potential between the two, you are imprinting a potential onto the graphene that matches the shape of your patterned graphite. In principle, you can also pattern your BN spacer. That will also change how much electric field reaches the graphene. So several people have done this, in large part Carodine's group. So here's an example of patterning the BN spacer. Then you apply a magnetic field and your backgate, and you see that suddenly there's like new features showing up intersecting non-zero. And this is because you have the superlattice from the backgate shining onto the graphene. The effects are subtle because the length scale is fairly large compared to where we want to be, 10 nanometers, but it's there. This is another study from a group in Germany where they directly patterned the gate, like I showed in the previous slide. And again, the effect shows up, but it's subtle. And you can start to play tricks where instead of making an array of holes, you can make something that is anisotropic, so like an array of lines. And this has profound consequences, because now your band structure is different also depending on which direction you're looking at, which is a lot of fun and another tuning knob to work with. But again, length scales are not great. So I showed you that the E-beam, the spots themselves are something like 2 to 4 nanometers wide. So why are we not doing 2 to 4 nanometer features? The issue is that real life is slightly more complicated than PowerPoint physics. It turns out that when these high energy electrons are hitting your sample, they are locally ionizing. So they are generating more electrons that travel a local distance next to where the primary beam hits. Those spots are something like 20 to 30 nanometers wide. And this is an intrinsic limit of EV lithography. So then suddenly you have something that is quite wide, you try to go and develop it. And as you try to move features close to each other, they start to merge together. So this is why we have this approximately 30 nanometer intrinsic limit with conventional EV lithography. Yeah, so this is what's it. Secondary electrons is like your biggest enemy in polymer-based EV lithography. So right now, people are working on, instead of using polymers, EV lithography, maybe you can use kind of exotic resists that directly evaporate when you hit them with the E-beam. Then there's not enough energy from the secondary electrons to cause that evaporation and so on. But this is very non-conventional and very much ongoing research. So can we do? Yes, absolutely.
If I understand correctly, you put your graphene on some kind of substrate, for example, silicon oxide, and pattern, and then etch with these holes. So during this etching process, you should remove certain layers of silicon oxide as well, right? Or both graphene and silicon oxide, right?
Yeah, depending on how you etch it, yeah.
Like, do you want that the case, or you only want the holes in graphene and substrate is more of a side effect?
If you're doing the approach where you are removing atoms, so etching the graphene, you really only care about the graphene missing holes. So you don't, it's not necessarily bad that you're etching the surroundings, but it's not the main intent. So if you didn't have to, that would be fine.
But you cannot avoid it, right? You cannot only control the E-beam to only etch one atomic thing.
So the nice thing is that this picture here, you can imagine that you have this resist, and then there's a layer of graphene sitting in between. If you use some etchants like oxygen, that will etch your graphene, but it doesn't etch the silicon oxide. Okay. So you can change the chemistry that you're using to etch, make it more selective towards one or the other.
But if that's the case, you don't have the HBN layer to the graphene and the silicon oxide, right? But I saw slides, you do have the HBN as a spacer.
Yeah, that's right. So in this situation, what we started out with was a resist sitting on top of this top blue layer. Then we used the E-beam to open up holes in that resist, and then we etch into first the boron nitride and then the graphene. It was kind of a multi-step etching to get down to the graphene. That also helps us because all of the polymer residues and all of this weird stuff that might be left behind is sitting on top of the boron nitride, so not touching graphene. And that helps a lot with quality issues. So it becomes complicated once you want to make an electronic device and you have to etch into it and make sure things stays clean. You see there's an etch angle to the BN as well, so you have to take that into account when you're etching. So if the BN is too thick, you're just going to etch like a cone into the top BN. It's not going to reach the graphene. So many kind of maybe not so interesting, but practical considerations to get something like this to work. Okay, so normal EV lithography, we have issues. Can we use a technique where it's only the primary beam that matters? So this is where we have this scanning tunneling electron microscopy. So now we are working with samples of suspended graphene. So you have this monolayer of graphene sitting with air on either side, and we're looking through it with the electron beam. But it turns out that if you use high enough energy for your electrons, suddenly the scattering cross-section for knocking out atoms directly with the electrons becomes quite high. So you can see as you're reaching the 90 to 100 kilovolts acceleration for your electrons, suddenly a feasible process is that you are carving atoms out of your graphene. So instead of using this technique for imaging, maybe we can just brute force knock out atoms, pattern or sculpt directly with the E-beam. This is, as you can imagine, a very slow process, but then we are not limited by some secondary electron scattering. We are just limited in spot size by the spot size of the E-beam itself.
This data is for graphene.
This is for graphene, yeah. So this is these two graphs are different isotopes of carbon. If you do other 2D materials like the TMDs in particular, they are much more susceptible to radiation damage. So you have to do, I mean, you get a higher yield of sputtering, which is why I think people use something like 80 kV or lower for imaging TMDs if you don't want to have like defects induced by you looking at it. So this kind of effort started maybe 10 years ago at this point, and initial results were quite promising. As you can see, you can really make extremely small feature sizes. This is 8 angstroms across. So here the beam has been scanned across the graphene here, and all of the surrounding is freestanding graphene with some amount of crap on top. That's why it looks like weird and amorphous. So this is one of the issues of making suspended samples. You have to do some kind of a wet process to make the graphene freestanding, which usually ends up contaminating the material. But since then, 10 years later, this is the state of the art right now for, in this case, punching holes into WSO2. This is from the group of Yannick Meyer. So here you have a periodicity of 5 nanometers, very small, well-defined holes where this scanning electron microscopy beam has really just punched out individual sites. This looks like we're basically done looking at something like this. That's the reason I'm telling you about it, because we're not done. It turns out that these kind of tools are extremely expensive, very delicate, very rare. It's not like an E-beam. Sorry, yeah, go ahead.
Yeah, how are you able to avoid secondary electron creation and other cascading effects?
So you don't avoid it, but the secondary electrons in terms of energy are like way out here.
Okay.
So they don't have enough energy to like, this is like kind of momentum transfer. You are literally knocking out atoms. So you don't avoid them, but they don't play a role.
But also usually the secondary electrons come from deep in your substrate, not from the first layer.
That's another point, yeah. As soon as you have something suspended, there's just less bulk to interact with. Yeah, so the secondary electrons I was talking about is the extra fast ones you get for the immediate knock-on damage. Then you have deep from the bulk, all kinds of secondaries as well.
There's a question.
Yeah.
So for, not sure, I guess how to phrase this, but so when you create these holes, presumably you're going to have some dangling bonds that that form.
Yeah.
Do you like introduce hydrogen or something to kind of cap those dangling bonds somehow, or do you just kind of let them be and it doesn't actually cause that much finishing disorder or anything?
Yeah, we just let them be. So this approach of making holes directly in the graphene to kind of measure the antidotes, I would say that's done with. What we're most interested in now is using these materials as the gate for something else, or as the dielectric or something like that. And in that case, we don't care too much if there's some dangling bond and so on. We just care about the fact that no electric field is going to emanate from the part where holes are missing. Maybe in, if we can make this really clean, stuff like that is going to matter as well for like nice field line profiles. But for now, we are like really just exploring how to make it work at all.
When making each of these holes, you just hold the electron beam steady while it goes through. There's no moving back and forth, up and down, or sweeping it while you're making each hole.
Depending on how big your spot is, you might, I think these ones are like moved in a small circle, what's called, circle around. But in principle, you could just keep the spot fixed and you get something like a 2 nanometer hole. But it is also a slow process if you want to make larger holes.
But the edge would definitely affect the edge, make the difficult, depending on why make the difficult data CPR apply, right?
Probably, yeah. I'm not exactly sure how. If you're not using this as the active material, but only as a gating material, I don't know how a magnetic field would affect this material itself. But at least for the graphene with holes in it, we saw that has a big effect. You have like states living around the circles and so on, and you get like commensurability.
The theory was based on removing individual atoms, right?
Yeah.
So why are you then creating, rather than just shooting one out with a single spot size, why are you then creating larger circles?
We basically don't have that control.
Okay,
Yeah, so the theory was not even individual atoms, maybe it's like 10 atoms or something like that.
Yeah.
Still much more than we can do, but you do need a certain size of the holes, even in theory, to get like a mix of the superlattice and a quantum confinement effect. So between two holes, it matters how little graphene is left as well.
Yeah.
Do we have a phrase better than holes for the future? Because unfortunately, we keep calling these holes, but we already have the word hole for something very specific, depending on the gate voltage.
Initially, it was called a nanomesh, or anti-dots, or dots, something like that. Yeah. Maybe, let's see. If it becomes a hot topic again, we can sit down and discuss something better to call it. Right now, it's slightly dead because Murray just took all the thunder, but I don't disagree.
Just write hole in italics.
Yeah. Yeah.
Sorry.
That's okay.
No, also.
That's fine.
Yeah. So in graphene case, you were trying to make the app, but this one is 7.4. So what's the motivation?
So here, we are never going to measure any transport in this material itself. It's going to sit in proximity to graphene. And once we apply a potential between the graphene and this material, there's going to be field lines going between the two everywhere except where there's a hole. And of course, like electrostatics, there's going to be some kind of a smearing and so on, depending on how far you are. But that's the idea, that this guy is going to imprint potential onto something else. Anyway, long story short, for the STM approach, the machines are very expensive, quite rare, and it's even rare that you can program the beam in the same way that you do for an E-beam. Sample preparation is kind of complicated. You need to have your graphene suspended on a chip with a built-in heater, because if you don't heat up your sample, then it becomes extremely contaminated just from the slight ambience that you do have in any TM system. So how can we speed up this process? We can, instead of punching holes with electrons, we can do something heavier. We're relying on momentum transfer. So let's have a larger momentum initially. This is what's the basis of helium-ion lithography. Instead of shooting electrons, you're shooting helium ions onto your sample. They're about 7,000 times more massive as electrons. So this process is massively enhanced in terms of efficiency as well. This is a simple schematic of a helium-ion beam microscope. You ionize a stream of helium atoms, and you accelerate them towards your sample. There's a lot of very complicated electronics going on in terms of focusing this stream of helium, but this is the basic principle. Just going to go through this quickly in 2% time. This works, again, to some degree. Very recently, a group was able to make down to 20 nanometer length scales into a pattern backgate that you then imprint onto a single layer graphene. The results look like this. As I mentioned, we clearly see that you have some superlattice effect. There's energy levels intersecting away from zero showing up. This is for a 47 nanometer device. And there's also another device in the paper, which is 18 nanometer. This should be much more interesting, but it seems like much less is going on. And it turns out, even for this helium ion beam, it's actually a bit too aggressive. So as you are knocking out atoms, you are inducing some disorder quite a distance away from where the hole is. You can see even in this image, like this is not a nice ordered crystal. This is very messy and disordered around. So it's really hard to scale this down beyond the 20 nanometer limit right now.
What about the hole size? Can you scale that? Or is that?
You should be able to. I think the spot sizes of the helium ion beam itself is also on the order of like a few nanometers. I'm not exactly sure why we don't see smaller holes in arrays show up. Yeah, it's a good question. It's a technique that seems to be quite promising, but it's also, again, with the STM, it's very expensive. It's a delicate machine. Not many people have helium ion beams sitting around for lithography. Again, sample complication, quite complicated. You need to make suspended samples because you're knocking out electrons from the top and down. And it seems to be a bit destructive in terms of patterning as well, which we're not interested in. So the new kid on the block, which is not based on any beams hitting a sample, it's a thermal scanning probe. So this is based on the concept IBM introduced when they asked the question, how can we make mechanical hard drives even more mechanical? Because that's exactly what people want. There's more moving parts in your hard drive. So they had this idea of using an AFM. Let's see if I can actually start it. Okay, so the IBM approach was to say, how can we scale something to the ultimate resolution in terms of lateral precision? Atomic force microscopes are already extremely good at this. So maybe you can somehow have an AFM that is both able to write information in a resist and then read out the resist afterwards. So what they proposed is to have some plastic sitting on your surface. So this is going to be your right medium. And then you heat up an AFM tip and you just indent into that resist. And then you have written either a 1 or a 0. And then you can, when you stop heating the tip, read out across the resist, do I have a 0 or not? That's very slow. So IBM managed to scale up this technique to something like 64 by 64 AFM heads on one surface, working in tandem to read out these complex patterns. Ultimately, the project failed because there are so many moving parts. That's already the issue with normal hard drives. But there was a nice spin-out technology of this project, which was that you can actually use this like heated AFM tape for lithography purposes. If we're not doing something scalable like hard drives, but just prototyping, this can actually be a very powerful tool. So the principle, as I like briefly alluded to, is based on an AFM. You have a fairly regular AFM tip. You have a cantilever with the tip here. This is controlled by some AFM software. You control the X, Y, and Z positions. And then you have separately heating electronics. So you can locally heat your tip. And because these tips are so small, heating is extremely efficient. You can turn on and off the heating very quick. That also gives you a feedback loop of measuring the topography and heating. So you have extremely high fidelity patterns because you immediately see what you have, and then the AFM can adjust how much it's heating, how much it's pushing down. And you can do what's called grayscale lithography. So in e-beam lithography, you either have your resist or you don't. Here you can choose how much resist you have and how much you heat and how much you push down on your surface.
So do you have a requirement for the probe material, like the thermal conductivity? Will that influence the result?
Maybe. I think the tips are fairly standard silicon with some kind of just a wire going through, so you can resistively heat it up. Because it's on the nano scale, you just need to like heat the tip up to a few hundred degrees, and then you're done. Maybe metals would work better, but I think doped silicon is already like pretty good heat for that. Yes.
So I guess since heating is diffusive, like you would expect that, I guess I would expect naively that you would have similar issues to e-beam lithography, where the heating of the surrounding resist, other than where you directly want to heat, weakens the resist in a larger area. So do you have resolution issues because of that?
Maybe at some point, but for now, no. So right now, this is a fairly young technique, and we are able to get something like 30 nanometer periodicities. And it doesn't seem to be limited by heating. It seems to be limited by the shape of the tip. It's kind of conical. So when you're pushing down, you get just larger features just in the shape of the tip.
Okay.
But if you repeat this with like ultra sharp AFM tips, maybe you get something like the heating being an issue.
Okay.
The good thing is that the kind of resists you're using for this kind of evaporation technique are special in the sense that you have a graph here which shows you the temperature at which the resist is heated, and then how much is remaining. And you can see it's a fairly narrow range between the resist being fully there and fully evaporated. So I think somehow this is also a saving grace in terms of like how far out the patterning itself extends. So this is the approach for using this technique. You have your some substrate, maybe a 2D material on top, and then on top of all of this, you have one of these resists that you can evaporate. You then come in with your thermal probe. You heat it up, you define some pattern in your software, and it just writes that pattern out and checks with the feedback loop of topography that you're getting what you want. And then you can evaporate metal on top, or you can etch, or whatever you want. This technique is extremely nice because it's a tabletop machine we're working with here. This is not even a fancy AFM. This is like medium grade AFM that's you can probably not buy it for your kitchen, but it's fairly inexpensive. It's just the heating that really does all of the heating and the software, the feedback loop. It's really the magic here. So this is an example of some early testing, etching patterns into boron nitride, where quite easily patterns down to 29 nanometers were achieved. And this was not pushed nearly. This is just early. So right now, the thermal probe lithography, it's up here. But it seems like with a bit of optimization, we can at least push it to the low 20s regime. And then you can start to play tricks like double patterning. Because it's AFM based, you know exactly where you are. So you can pattern your resist multiple times or your device multiple times. So you can do double patterning and triple patterning and so on, because everything is aligned. So even just doing double patterning, you gain a square root 2 in density. And then suddenly we are down here where things start to be interesting. So I think this is a technique that you should kind of like keep an eye out for. Yeah.
Oh, never mind. I was going to ask how you would be able to do that if your resolution is the issue. But your resolution isn't getting the AFM tip to where it is. It would be some heating or some tip characteristic.
Yeah, it's more processing related.
Right.
How fast pattern compared to EV?
So this is very fast. So you can pattern a fairly dense 20 by 20 micron area in a few minutes. It's more or less as fast as doing an AFM scan normally is. So you can go slower if you want, maybe a bit more resolution, but it's on the order of AFM time. And it's done in the ambience, and it's all very easy. Just plug in your sample, ready to go. I'm going to go quickly through the bottom-up approach. Just mention that there's this kind of beautiful technique based on what's called block copolymers. So in lithography, we have these nice chains of monomers where all of the chains are the same type of polymer. But you can play tricks where you then maybe have two types of polymers connected to each other. And if these different chains have different surface energies and different like mechanical properties, you can really get a diverse array of different structures to form. So this is like a phase separation. If there's different energies involved, the two ends, they will separate somehow. And depending on the length ratios of these guys and how you treat the surfaces they're sitting on, you can get, fancy 3D structures, 2D structures, lamellas, interesting kind of things. The idea is that you take your bottle of nice block copolymer, you spin it onto your sample and bake it. You get something nice and aligned, and then you can selectively remove one of the two polymers, depending on the solvent you're using. And then, you can do this for 3 polymers and 4 polymers and so on, and get very complex shapes. And then if you do this right, you can get fairly aligned structures down to the 20, 15 nanometer length scale. But you can already see here, so these are some guiding structures to kind of help the resist stick out, so you get holes embedded in the matrix. Here you get lamellas, and it's clearly very dependent on the local environment. And this is even more evident here. So this up to down is the same resist, but just different thicknesses. And you can see how just like slight changes in the thickness of the resist completely changes the morphology. And then if you have like slight changes in the ratio of the two ends of the polymer, that also changes your topology. So this is a technique with a lot of potential, but it's extremely messy, extremely complicated. A lot of surface energies to balance out and make work. And then you go to another lab, and then, you know, because humidity is different, everything is different. So you don't want to do this, but it does exist. You need to look up the literature. Another thing you can do, the fine bottom-up approach, is self-assembled nanospheres, for instance. So instead of having to rely on like this very complex surface energy interactions, you can just take people can do this. You can take a bunch of very uniform spheres, and you can kind of force them to be nicely packed together. And that doesn't rely too much on surface interactions. The trick here is how can you make sure you only get one layer of spheres and not like many layers. But again, we have issues with long range order. It's clear here that the length scale is something like 200 nanometers. There's maybe order on the, a few hundred nanometers at most. And this is already pretty good. I'm going to skip the hybrid approaches, but you can start to play tricks with, top down and then combining that with bottom up, where you are etching holes into, for instance, a TMD, and then using chemical processes to kind of grow these holes in crystal directions. You can get like very dense and fine features out of that. You can do strain, kind of have strain as a tuning knob for your band structure engineering. This is also nice. So this is my conclusion slide. It's worth keeping an eye out for these techniques still, because process and progress is ongoing. And at some point, we are going to get down to this regime. And then something like E-beam, where you can tune exactly the symmetry of your pattern, where the holes are. You have perfect long-range order. It's really going to be an interesting tool to engineering band structures in 2D materials. Moray is really the hot topic, the new kid on the block. But even Moray physics has some issues with long-range order, especially as you are increasing the periodicities to something like the 10 nanometer scale. Long-range order is a bit iffy. This was recently highlighted in this review in Nature, kind of like stating some of the issues that we have in the field in terms of reproducibility. It's not called a crisis yet, but there are a lot of very high-profile papers showing extremely interesting physics that is not reproduced by any other group at this point, which is, should be like a red flag for a lot of this. I think we might have some of the solutions to this, but Mael, sitting here, will tell you all about it on Friday. So if you stick around, it's going to be a fantastic talk. And that's it. Thank you for your attention.
Lots of questions. For the helium irradiation, what was the energy that includes the mesh?
I actually don't know. I can look it up, but top of my head, I don't know the energies involved.
But so does it like? Do you remember this? That it does it the distortion along the transverse direction, does it depend on energy?
It might depend on energy. So my interpretation of this, like damage that you get away from the hole, is that it's like really a physical, like there's so much energy deposited into knocking out atoms that it distorts the lattice away from the knockout side. So maybe by tuning the energy, it's possible to kind of mitigate some of that damage. I've also seen reports about heating up your sample while you're doing this. That can somehow help kind of heal these lattice distortions as they're happening. But then it's another complication on top. So yeah, I'm not an expert in the helium ion, so I'd be happy to look it up if you're interested.
Nick, so on this slide, I don't know if this is a dangerous topic, but reproducibility. This is reproducibility in the fabrication. So is it a consensus that
it's really, how you're putting things together as opposed to how you're measuring.
My interpretation is that it's really the application that's the issue. Maybe I should have shown how we make these, but it's kind of a rough process. Like you have, as Jim showed, this exfoliated 2D material on your surface, and then you come in mechanically with another 2D material. You just kind of make it stick to that 2D material. You rotate, make another part stick to that 2D material, and any kind of strain or disorder that might be from the graphene, for instance, on silicon oxide, to some degree gets translated onto the BN. This low twist angle regime, there's also a lot of friction that helps to kind of pin any kind of disorder that you start out with. But I mean, many of the reasons for all of this disorder is not well understood. It's also not well characterized.
And it's kind of clear how you would characterize it. It just really hasn't.
It is clear. It's mostly an equipment issue. So many groups doing fantastic transport studies doesn't necessarily have the tools needed to go in and image what is a 10 nanometer array pattern looking like. It would be fantastic if we had more of a correlation between the two, because for sure there are papers in the literature where something else is going on. Maybe there's an extra array interaction between the graphene and the BN that really does the thing, but it can be subtle, so subtle that it doesn't show up easily in transport, but it might be that.
I can add. So this is all kind of local strain and stretch, right? And we have good techniques based on scanning probe to image the moire patterns and understand what this strain disorder is. But then when you make the encapsulated device, you go blind again. So that's the problem.
So could you use this this AFM thermal technique to maybe very locally anneal sample, and could are there applications for that, or are there reasons why that wouldn't work so well?
I think that's a great idea. So for instance, some 2D materials, if you heat them up too much, it just evaporates. So maybe just directly pattern your 2D material by look at the heating enough, it evaporates in that region and you're done. Local annealing, I don't see why not. I'm not exactly sure what the temperature limit is for this technique, how high you can go locally before things become messy. But I think there's a lot of interesting local thermal treatments you can do in this regard. Maybe you can heal some defects or evaporate the contamination.
Yeah, that's what I was thinking, because our materials are often crappy, and we try and figure out ways to fix our defects.
Yeah, exactly. It's just so young, we don't really know yet what is feasible, what is not. But the fact that this is just AFM with modifications gives a lot of hope to kind of go wild and just try some things.
Thank you.
Sure.
Is there a question? Yeah.
So when you are removing the carbon atoms, creating those holes, so I'm wondering, where are those atoms go? Did they redeposit? For example, you use STM, so you expose the graphene layer. Where do those atoms go? Do they redeposit on the film again and create some?
So I think the amount of atoms you're removing is very low compared to even the low pressure that you have in your chamber. So one of the biggest issue with STM is not the kind of spotted carbon redepositing. It's just stuff from the chamber depositing. So my interpretation is that the atom just kind of gets pumped away or gets mixed into whatever residual atmosphere you have. So because it's one layer of atoms we're working with, or maybe a few layers, even if you remove some atoms, it's in the grand scheme of things vanishing small amounts. So it's not in normal sputtering of substrate where redeposition is really an issue. We don't have several nanometers. We have at most 1 nanometer. Getting removed.
Yeah, and then AFM, what mode are you offering AFM in?
So this is contact mode. So it does a double pass. So it does one mode in tapping mode for topography, and then it goes in contact mode and turns on and off the heating where it needs to do some kind of an indent.
Okay, so do you ever have issues with building material on the tip? Because even doing a normal tapping mode, you can get building material on AFM.
Yeah, you do.
And so I can imagine with heating.
Heating, the nice thing is that you can kind of go away from your sample, crank up the heat, and then kind of blast away some of the stuff you pick up. But it is one of the, I think you go through more tips with this technique than you normally do, but it's not 10 times more, maybe 2 or 3 times more. Also the sharpness of the tip, right, degrades fairly quickly, so that can influence as well.
Yeah. Any final question? Are you hungry? Oh, one question.
Maybe one, sorry. It really made me curious about this like what was train. So could you give me like a 30-second pitch about the principle of that one?
Of which one? Sorry.
The strain.
Oh, the strain. Yeah. So, so this is, I don't know if the speakers here yet, but Eva Andre has really shown that you can get incredibly interesting electronic properties of graphene by straining it. So in that particular case, the graphene was put on some material with another thermal coefficient of expansion. You heat it up, you do like a thermal cycling, and then when the graphene is kind of releasing the strain, that matches the message mismatch between the 2 layers. So then you get like some out of plane corrugations of the graphene, much more than you do normally with just like Moray physics. And it turns out to give you like, you know, flat band physics and like kind of beautiful SDM results. I don't think it has been done in transport yet, but it is kind of an interesting approach as well.
Okay, I guess we are hungry now. Okay, so thank you very much. So we have lunch downstairs. We should have one. And then around 1 o'clock, or 1:15, let's say. Everybody gets ready.